Welcome back, ladies and gentlemen. Today we're going to talk about section 5.4 dealing with medians, altitudes, centroids, and orthocenters. As usual, you'll see your exit question up on the screen. So far in this chapter, we have taken a triangle and we have constructed certain pieces of it. We've constructed the midpoints of each side, the perpendicular bisectors of each side, and the angle bisectors. With the midpoints, we connected each midpoint. With the perpendicular bisectors, we notice that there's a point of concurrency, and with the angle bisectors, the same. So using those ideas, we constructed mid-segments, something called the circumcenter, which was our first point of concurrency, and something called an incenter, which was an additional point of concurrency. Each of these constructions resulted in certain properties of each of those objects. So we got the mid-segment theorem out of the mid-segments, which actually had two conclusions. We had the fact that the circumcenter is equidistant from each vertex, and we had the fact that the incenter is equidistant from each side. Today I'm going to give you two more constructions and give you two more concurrent points. The first one we're going to tackle is dealing with medians. Okay, and a median is a pretty simple line to draw. The only thing we need is a midpoint again, but instead of connecting midpoint to midpoint, we're going to go midpoint to another vertex, or the opposing vertex. So without further ado, let's go over to GeoGebra and I'll show you how that's done. Here we are in GeoGebra, and I've got my polygon tool ready to just start making a triangle here, so I'll do that. Again, a median is connecting a midpoint to a vertex, so I'm going to need to find the midpoint of each side. So under the point tool, I can construct a midpoint if I select a side or 2 points. So I'm going to select all three sides, create all three midpoints there, and then I'm going to use the segment tool to connect the segment, the midpoint to a vertex, to its opposing vertex. So I'm going to go from midpoint to opposing vertex, and again midpoint to opposing vertex. And you might not be too surprised to notice that, hey, look at that, we've got a third point of concurrency. Okay. Now, as with all of our other points of concurrency and mid-segment theorems, there are some unique features to this point. This point is called a centroid, so a new vocab word, and there are some properties about that centroid. So give me a moment and I'm going to reformat this so it looks pretty and so that we can measure things. All right, that looks better. Now, firstly, before we get into what I've done here, I want to point out that if I move this triangle around, so if I have obtuse, approximately a right, or acute triangle, you'll notice that this point of concurrency, the centroid, is always located interior to the triangle. So that's an important point. And then secondly, I have all three medians drawn here, but you'll notice that the centroid itself kind of segments each median into two segments. Okay, so I've highlighted one portion in green and one portion in blue, and then I've had this program measure the distances of those segments as well. Now, there is a mathematical relationship between these two, and you'll notice that if you take 5.7 and double it, you'll get 11.4. So there's that 1:2 ratio that's happening within this triangle, and that will always occur no matter how I stretch this triangle to be. So we've got 7.5 and 15.1. Obviously there's a little bit of rounding. There it is more accurately right there. But you can notice that no matter how I manipulate this triangle, the green segment is always half of the blue segment. Now this has a little bit of asymmetry to it, so the longer piece is always the one that extends to the vertex, and the shorter piece is always the one that extends to the midpoint, and you just have to be able to get that straight. As you might suspect, there's a theorem that states basically all of these properties. And if we go back to our slideshow here, you can see that we have the official definition for the centroid, which is a concurrent point at which all three medians intersect. And there's the definition of median again, and this is how you construct it. And of course, then we have a theorem. And the theorem says that one, that the centroid exists in every single triangle, and secondly, that there is that ratio, proportion, however you want to think of it. So the way I think of it is that the green segment is half of the blue segment. The other way to think of it is the whole segment is made up of three pieces that is 3 times the length of this green segment, so 3 times the length of dp. So In other words, DP is 1/3 of the entire length of the median. So however you want to think about that, you may. So you can think of the blue segment being 2/3 of the entire distance. You can think of the green segment being 1/3 of the entire distance, or you can think of the green segment being 1/2 the distance of the blue segment. And the other thing I'll point out is that by nature of this, it's kind of an optical illusion. You would not think that this blue segment is twice as long as that green segment just kind of by looking at it. But again, as you've measured and as you saw on the GeoGebra, that is indeed true. Now moving on, the centroid is actually kind of a special thing in terms of the real world. The centroid, if you find the centroid of a triangle or a triangular prism, it's actually the center of mass, and this is one way that they can find the center of mass of actually irregular shapes too, by chopping it up into little triangles, finding the centroid of each triangle, and then finding the average position of those centroids. So the centroid is not only the center of mass for any triangle or triangular prism, but you can also extrapolate that and find this center of mass of a more irregularly shaped object. Next up, we have our very first example. This is a pretty difficult example, and it's also awfully close to a test question, so I'd highly recommend pausing the video here and writing down the given information. Okay, in this example, you are asked, or you're given a triangle with the vertices given to you, and you are asked to find the centroid. And not only are you asked to find the centroid, but you're asked to justify that the point that you found is actually the centroid. So we basically have two goals here. One is to find the centroid, so we're going to have to draw the medians. And then on the graph, if we do that, we're going to have an apparent intersection, but it's not for sure. So we have to show through algebra or through some other sort of proof that the point that we found is indeed the centroid. So the first step to drawing the medians is to find the midpoint of each segment. So apply the midpoint formula. Or you can actually just do kind of a rise over run thing here. You notice that we're over 2 up 4, so the midpoint would be over 1 up 2. You do that to all three and you get the 3 coordinates of the 3 midpoints. Then construct the medians and you have a drawing that looks more like this. Now here's what I was talking about, that you have an apparent intersection at C, and it's going to take a little bit more work to say that C is for sure the centroid. You know, this is right now it's just a drawing, and even though it looks like it very conveniently landed on 4, 5, we don't know for sure because there's some error in our drawing. It might just be really close to that point and maybe not for sure that point. So one thing that we have to do is we have to prove that it's a centroid, and to do that we're going to show that the distances fall along those same ratios as what was discussed in the theorem. Now that means that I have basically 3 choices. Now it is enough to show the small piece is 1/3 of the whole piece. It's enough to do that just one time because the theorem says that the centroid exists in every triangle, and that centroid will be exactly 1/3 of the way across the median. So there's 2 easy ones to do and there's 1 difficult one to do. So you notice that 2 of the medians happen to be, one is vertical and one is horizontal. So if I can just do the distance, now if this weren't horizontal, like say this one, I would have to use the distance formula to show that the distance between H and C is twice that of CD. But as it stands in this problem, we have a nice convenient horizontal line and a vertical line. So AC is 1, so this distance right here is 1, which is half of this distance right here, so therefore it must be the centroid. Or you could have gone, this distance right here is 2, which is half the distance here, which is 4, so therefore again the centroid must be 4, 5. I want to point out that this problem could have been a lot more difficult. One, that intersection might not have been so apparent, it just happened to line up right on 4, 5. And secondly, 2 out of our 3 medians were perfectly vertical and perfectly horizontal. That might not always happen, so you might be in a situation where you have to use the distance formula. Moving on, our next item of business is an altitude. So I'm going to show you a second construction today dealing with altitudes. An altitude is a segment that's drawn from the vertex of a triangle along a perpendicular path to the opposing side. And I have two examples drawn here, one with an acute triangle, one with an obtuse triangle, basically showing that an altitude is not constrained to be on the inside of the triangle. So with an acute triangle, if you drop directly from, so this is like the line that you would use to find the height of a triangle if you're trying to find the area of a triangle, that's the altitude. If you were to drop from the vertex to its opposing side along a perpendicular path, this would be, it would end up being inside the triangle. But if you do that on an obtuse triangle, for instance, you'll notice that you have something that's on the outside of the triangle. Again, we're going to do a construction in GeoGebra. Now this is one of those constructions that can get awfully messy awfully quick, but I'll show you the gist of it, which is if we want to draw a perpendicular line, I need to know a point to go through, and I need to know a line as reference so I know what to draw perpendicular to. So you'll see that it drops a perfectly perpendicular line to the side that I selected, and if I do that 2 more times, it will do the same thing. So that point and that segment. Now you'll notice that these lines do not intersect on screen, but if I move it around a little bit, you can see that that intersection does indeed occur. So we have yet another point of concurrency right there. Now the only thing that you need to know about this point is, so this point of concurrency constructed from the altitudes is that one, it exists and it's called the orthocenter, and the only other thing you need to know is about its location. So right here we have an acute triangle and it is located inside the triangle. Now I have a right triangle, and you notice that the orthocenter has moved to be on the vertex of the right angle, so that's kind of a weird place for it, but it's there. And then lastly, if I have an obtuse triangle, then the orthocenter is outside of the region. So that brings us to our last theorem of the day, and it's a theorem that simply states that the orthocenter exists for every triangle. And there's your official definition of orthocenter, which is the concurrent point at which all 3 altitudes of a triangle intersect. And it might be helpful to know that the word orthogonal is yet another word for perpendicular. Also, keep in mind these rules, that if you have an acute triangle, the orthocenter is inside the triangle. If you have a right triangle, it is right on the right angle, so the orthocenter is right there at P. And if you have an obtuse triangle, the orthocenter is going to lie outside of the triangle. So that is it for our collection of concurrent points. And you can see we've kind of got this new table here with the new stuff highlighted in yellow there. We've done medians, which creates a centroid, and you get these rules of 2/3 to 1/3 ratio. We have also done altitudes. That's called an orthocenter, and all you need to know about it is that it exists and the relative location of it in different types of triangles. That's it. That's a great summary of the first 4 sections of Chapter 5 right there. Up on the screen, there's your homework, and I'll see you in class.